Okay, this is not going to be a wonderfully professionally prepared video, but this will serve as a replacement class for Monday if we lose classes due to snow. So today, Monday, today, we're going to cover infinite limits and infinity. And they're written differently because infinite limits is talking about y going to infinity or negative infinity, whereas infinite limits at infinity is talking about x going to infinity. Okay, so let's just a few reminders just to get us started. All right, we have one-sided limits. Those are limits from the left or from the right. So left or right. And then we also have two-sided limits. And the important thing for two-sided limits is that they exist, they have an answer, if and only if the left-sided limit equals the right-sided limit. So let's move on. So we have two-sided limits that exist if and only if the right limit equals the left limit. So importantly, if the left does not equal the right, then we're going to say that the two-sided limit does not exist. Now, I know many of you have been taught that infinity does not exist, and while that's true, if we find that the left-sided limit is going to infinity and the right-sided limit is going to infinity, we are not going to say that the two-sided limit does not exist. We're going to say that the two-sided limit also goes to infinity. So we're going to reserve do not exist for when the left limit does not equal the right limit, the right-sided limit. Okay. So let's get started then on infinite limits. Okay, infinite limits really applies to rational functions. So when we say infinite limit, we're talking about y going off to infinity as it approaches a very specific point. So we're not talking about the fact that x squared goes off to infinity as x gets large. We're not talking about that. So a rational function, remember, is f of x, the base is 1 over, the base function is 1 over x, to any exponent. So the first one we're going to look at will be f of x equals 1 over x. Now, you may remember, hopefully, what this looks like, or you can use your calculator to graph, but we know it looks like this. We know that that the domain is that x is not equal to 0. We know that there is a vertical asymptote at y equals 0. And we know that there's a horizontal asymptote at x equals 0. Okay, so now let's consider our limits. Particularly the place of interest is going to be x equals 0. So first we'll look at the right-sided limit as we go towards 0. So here we're letting x get closer and closer to 0. That means I track the shape of the curve as x goes towards 0. So what's happening? That's heading off to infinity. I like to use an arrow because actually we can't write equals infinity because there is no value. We don't know what it is. All right, now let's look at what happens on the other side, looking as we approach 0 from the negative side. So again, we're going to let x go to 0 this way. So we're going to track the curve as we go that way, and we see that it's headed towards negative infinity. Okay, so these two do not agree. They are not equal. So we're doing one thing from the right, a different thing from the left, and so that means that our two-sided limit, we can't say which one it is, so we have to say that it does not exist. So we can back this up then and look at it the other way. We can say that if we have a limit as x approaches a finite value, and it goes to plus or minus infinity, that necessarily defines the vertical asymptote. So let me write that out. If we say the limit as x approaches c of some f of x. So we're getting very close to a finite number, and as we do, the function goes screaming off to infinity or negative infinity. So if this goes to either one, on either side, or both on the same side, then this defines a vertical asymptote. Okay, so let's do another example. This is example 2. And the example numbers match the notes that I've posted online as well. So we have f of x is 1 over the quantity x plus 2 squared. Okay, so first let's get a graph, again, just so we kind of know what we're thinking about. You will remember that x squared, 1 over x squared, looks something like that. The plus 2 on the inside, that's going to affect the x value. So it's a right-left shift. That will be a negative shift. So that means, in fact, we know that x cannot equal negative 2. That's our domain, so we know that's the location of our vertical asymptote, right here. I'm sorry, it's a little bit wet. Okay, so again, now let's look at the limit as x approaches the value of interest, negative 2. So if I look at the limit as x approaches negative 2 from the negative side, 1 over x plus 2 squared, and I'm going to look also from the right side, and let's see what happens. Okay, so from the left side, we're going to be coming from this direction, and so we're approaching negative 2 from the left side. So as we're tracking x this way, we're tracking the y value along the curve. So the y value, oh, I drew this wrong. There you go. Try that again. 1 over x squared looks like this, so just shift it over. So now, as I'm tracking x going towards negative 2 from the left side, I'm seeing that the y value goes off to infinity. I can do the same thing from the right side. As x is approaching negative 2 from the right, I'm going to track the curve and see where it goes, and it also goes to infinity. So because these agree, that means that I can say that my left-sided limit as x approaches negative 2 of 1 over x plus 2 quantity squared goes to infinity. And so that's a behavior. Yes, I know infinity does not exist. We can't actually write the number for that. But we know that this behavior is doing the same thing on both sides. So we know what it's doing. From the two sides, we know where it's going, infinity. Okay, so again, because we can write it this way, this defines the vertical asymptote. Because as x approaches a finite number and the limit goes off to infinity, that tells us that there's an asymptote right here, a vertical asymptote. Okay, so now we need to look at some arithmetic using 0 and infinity and n. And so there's some things that we know, we've been taught for a long time, and then other things that are going to be a little bit new to us. Okay, so let's look at some arithmetic with 0 and infinity. Okay. 0 divided by any finite number. We've known for a long time that that's equal to 0. We need to keep that in mind because we're going to be looking at some other arithmetic involving 0, and sometimes it's easy to lose sight of the fact of what we have known for a long time. So let's keep that there. If we take n and divide by 0, well, we know we cannot divide by 0. So what happens is you take some number and divide by a smaller and smaller and smaller number. It's like saying how many pieces are there, but each piece is getting smaller and smaller. The number of pieces is getting bigger and bigger. This is going to go to either plus or minus infinity. Infinity times n. Well, if you're infinity and you make it twice as big, you're still there. So this is actually also infinity. Infinity plus or minus n. If you add or subtract a little bit, you're still way out there. You're still out at infinity. So infinity is this kind of weird moving target. You can't put a number on it, but we know that if we make it bigger, it's still infinity. If we subtract just some constant, just some small numbers, it's still out there at infinity. All right, what about this one? N divided by plus or minus infinity. So now we're taking a finite number, say 2, and dividing by an infinite number of pieces. How many pieces are there? Well, if there are an infinite number of pieces, the size is 0. Or you can think of it if you divide into, well, let me just say it, this is equal to 0, or rather, it approaches 0. Now, here come the interesting ones. Infinity over infinity, 0 over 0, infinity minus infinity. Sometimes when you remember, the first step in limits is always to plug in the value first. So if you get infinity over infinity, you might be inclined to say, well, any number divided by itself is 1. But we know that any number divided by infinity is 0. And we know that any number times infinity is infinity. So it's hard to know how to interpret this. Same thing with 0 over 0. We know that 0 divided by a number is 0. But I can't divide by 0, I get infinity. But any number divided by itself is 1. So what do I do with these that seem like they have many different values? These are called indeterminate forms. And they really can have any of those values, from negative infinity to infinity. It depends on the problem context. Typically, we're going to encounter this in this class with regard to rational functions with polynomials. And so typically, these indeterminate forms are going to result, particularly this one, from a hole in the graph. And so really, 0 over 0 can mean a lot of different things. That is true. It's a little bit hard to get your head wrapped around that, maybe. Infinity minus infinity. Well, 1 minus 1 is 0. But over here, I said infinity plus or minus a number is still infinity. And so again, this one also depends on context. It depends on how big the infinities are. I know that seems kind of strange. If one of these infinities is from x squared, and the other is from x, when x gets really big, this one is still much bigger than this one. So we'll get to that later. This is for the next section. But just so that you know, anytime I have a number, I know what happens with 0 and infinity. But anytime I have combinations of infinities and zeros, I'm not quite certain what they are, and I have more work to do. Okay, so now let's look at limits as x goes to infinity, and then we'll do several examples. Okay, so first let's just, this is example 4 in the notes. Let's just consider an example and see what we can make of it. So let's start with f of x equals x squared minus x. What does that look like? Well, it's a quadratic. We know that much. I can factor it. So I know the zeros are at x equals 0 and x equals 1. If you remember, your vertex is at x equals negative b over 2a. So negative of a negative 1, 1 over 2. So this is going to happen at 1/2, which is not, I mean, you expect it to be halfway between your zeros. So this curve will look like this. It comes through here at 0 and here at 1, and it has a vertex there. So there's our parabola. Okay, so now let's say what happens as, let's look at the limit as x goes to infinity of x squared minus x. Well, the first thing we always do when we have limits is try to plug in. So if I try and plug in, I'll get infinity minus infinity. I've already decided I don't know what that means. So let's come back to the graph. X approaching infinity is what sometimes we refer to as end behavior. What happens as we go way out here to the end? Well, clearly, as x is going way out here, we track our curve, and it goes on forever. So we know the answer to this is actually infinity. We know that because we know by looking at the graph. So how can we make this into that without looking at the graph? And so here's the deal. The important part of this is that as x goes to infinity, the only thing that really matters is the leading term. The limit as x approaches infinity is the same as the limit of the leading term only. So that means that this function here, this limit, we rewrite it, limit as x approaches infinity, of x squared minus x. All I really need to know is the leading term. So this is exactly equal to this. So now if I plug in infinity, infinity squared, infinity times infinity, all infinity. Another way to look at this is when x gets really large, x squared is going to be much bigger than x. So if we take x as 100, we'll get 10,000 minus 100. That's fairly inconsequential. If we go even more, if we say a million, that would be a million squared is a trillion minus the original million. Again, very small number compared to this very giant number. So really what we're saying is that any number that's small, any term that's less than the leading term becomes terribly small when we go out to infinity. So we can just ignore them for the limit. It's important to notice that this graph and this graph are not the same, but where they go as x gets really large is the same. So that's an important distinction. Limits are always about behavior and approach, not about exact values, not about exact functions. So in this case, the limit of this and the limit of this are exactly the same. Okay, now let's look at this again and look at rational functions. So this was a polynomial function. We can look at the same behavior for rational functions. Okay, so we're going to look at example 5. From the notes, this is rational functions. Okay, so let's look at our first one. F of x equals 2x over x plus 1. So what we want to know is, what is that limit? What is the limit as x goes to infinity of 2x over x plus 1? Okay, there are a couple of things we could do. We could graph it. That would be one thing. We could just do a little table of values. Start with maybe 100, 1,000, 10,000. See if we can figure out what this is doing. So let's do that. So this will be our f of x value. So if we put in 100, we'll get 200 over 101. So let's go ahead and, my calculator is stuck. All right, so 200 over 101, so this is going to be a little bit less than 2. If we put in 1,000, we'll get 2,000 over 1,001, even closer to 2. 20,000 over 10,001. You can see that that 1 is getting to be a smaller and smaller piece of the final value. And so if you will actually find the decimal values of these, you'll find that they're getting closer and closer and closer to 2. So we know that this is 2 just by doing some work this way. So how else can we think about this? Well, again, this is kind of like end behavior. Let's go ahead and get a graph of this. So I know that I have a vertical asymptote here, and I actually know that I have a horizontal asymptote here. We'll get to that in a second. Okay, so it looks like this. There we go. I knew something wasn't quite right. So that's what the graph looks like if we were to graph it on a calculator or do some work. And so this comes through at -1, and that will be a horizontal asymptote at 2. So let's look at how these go together. So one of the things we can think about is that x gets really large. This +1 really doesn't matter compared to the x. So we can write this, again, just looking at leading terms. And you may have remembered this from pre-calculus, where I say just take the leading terms, the ratio of the leading terms. But this is why. Because when we take the limit as x goes to infinity, these numbers get very, in particular in the denominator, this gets very, very big, and this stays very tiny at 1. If Donald Trump loses $1 compared to his however much he's worth, or Bill Gates, however many billions he's worth, the $1 doesn't really matter. And so we can look at this as this. We can look at only the leading terms. Well, now this is simply equal to, I can go ahead and do the division, 2. But the limit of any constant is just 2. So this defines a horizontal asymptote. If the limit as x goes to infinity of any function is a concrete value, k, c, whatever the number is, then y, remember these are y values, y equals k is the horizontal asymptote. And again, the idea here is that just like with polynomials, when you're looking at x going to infinity, the only thing that matters is the biggest term in the top and the biggest term in the bottom. Here in the top we only had 2x, so it stays 2x. Here in the bottom, x is the biggest term, so that gets translated, do a little bit of cleanup, and find your limit. Okay, so what happens if you don't get a number here? If you don't get a number here and you get, say, infinity, an example would be if we wanted to find the limit as x approaches infinity of x cubed over x plus 1. The same logic applies. That plus 1 pales in comparison to the x, so we're going to ignore it. So now we'll get x cubed over x. Well, when I simplify that, I'll get x squared. That goes to infinity. That means there's no horizontal asymptote there. So you have a horizontal asymptote, the limit as x approaches infinity of the original function must go to a finite value. Okay, so now let's take a look at several examples. And before we do that, let's take a look at what are all the steps we need to take to solve, to evaluate limits. And I'm going to write them over here so we can refer to them. Okay, so the first one is always make sure that you're using the right piece. So from the graph or from a piecewise function, make sure, particularly for left and right limits, that you're using the correct piece, the correct definition. If you're doing two-sided limits, remember that you may need to look at the right and the left separately. And that occurs really when you are at a vertical asymptote. Or if you're at a piecewise function right on the edge of the definitions. So here, if you have a two-sided limit, we may need to compare right versus left. So that means that you'll need to actually set up the two separate limits. Okay, so once we kind of know what direction we're headed, the first thing we always are going to do is substitute the x value. If you get a finite number, you're done. That is the limit. So if the answer is finite, some number, then you are done. On the other hand, if the limit is an indeterminate form, say 0 over 0, that means you have more work to do. And what more work is that specifically? Specifically, that means for us, because we're typically running into that with rational functions with polynomials, you need to factor top and bottom, cancel, and then substitute again. Okay, so that was what we did last time. Now what have we added? Now we have added some extra pieces. If when you substitute, you get something over 0, n over 0, you get some plus or minus infinity. Because you're going, again, these ones right here are for x approaching a finite number. If that's the case, then you know, if you're going to plus or minus infinity as you're getting to a finite number, you know that you're looking at a vertical asymptote. So that means that you need to consider the two sides separately. So that means that you need to do right-sided versus left-sided. Sometimes they agree, sometimes they do not. And then lastly, so these ones are all x approaching c. Now we're going to look at what you do if x approaches infinity. That's a different thing. Here we're going to look at just leading terms in both numerator and denominator. So only the leading terms. Let's see. How do I want to say this? You want to rewrite with only the leading terms. And then go ahead and finish, simplifying and then substitute again.